Hey everybody, my name is Corey Beard. I'm a graduate student at UC Irvine. And I'm here to talk about my project, which is called Simultaneous Observations of Kepler Objects with TESS NEID. Now, I'm gonna do this one really quick because we've talked about this problem a lot, and that's the fact that mitigating stellar variability is really important for the future of EPRV science. Fortunately, we can learn a lot about RV variability from photometry specifically. It's not just for transits. In particular, you see a lot of the frequencies and rotational signals in photometry that then imprint themselves in RVs as well. They're not exactly the same, but you see a lot of patterns there. What's even better is if we can get simultaneous RVs with photometry. This paper and even plot has shown up a little bit in some previous talks as well, but I want to highlight that this is a plot taken from Haywood et al. 2014, where they got simultaneous RVs with Core 07 photometry of a couple of planets. And what's particularly interesting here is that they were able to take this region of photometry that was simultaneous with RVs, and they were able to create a sort of predictive activity model. And this was actually a really important and helpful step to eventually characterize the masses of the planets in this system, which I think is really impressive, especially considering that the stellar variability was considerably larger than the planet amplitudes, or maybe not considerably larger, but a fair bit larger. Now, one issue is that there's a lot of different ways to use photometry to inform our RV models about stellar variability. I list a few here, but they are not meant to be exhaustive. You could do a frequency analysis, basically periodograms or autocorrelation functions. These can tell you useful information about frequencies, and they are really fast and they're widely used, but they can't tell you even close to everything. A more sophisticated method that a lot of people have done is to train models on photometry and use that to inform RV variability models. This can tell you a lot more than just frequency. It can tell you about decay time scales and things like that, but it can be expensive, especially since photometry data sets are oftentimes very large, especially compared to RV data sets. Jointly modeling is another strategy that people can use. This is even more computationally expensive, unfortunately, but it can shed light where some methods haven't, and it is, of course, used. Now, to make things worse when we're dealing with photometry in RVs, the optimal photometric data set is not always clear. I include a little summary of Kepler, K2, and TESS, which are not the only photometric data sets in town, but they are commonly used ones. Now, these data sets, as you can see, and many people here know, have a lot of differences. They were taken at very different times. They have very different precisions, band passes, and perhaps most importantly, observing baselines and observing strategies. This can have a big effect on how we want to use these when dealing with radial velocities. Now, I've started to design an experiment where we want to answer a few of the following questions I've just motivated. The first of which is, what is the best way to use photometry to inform RV variability? This is not an obvious question with an obvious answer. Second is basically which photometric data set should we be using when we are doing this? Maybe you want to use TESS and Kepler, but that can be computationally expensive and it may not be obviously the best way to go. It could be that spot lifetimes or different activity complexes have evolved in the 10 years since Kepler's been up. Another thing we want to quantify is the importance of simultaneous RVs. It's been mentioned in some previous talks that simultaneous RVs are really nice, but they are actually quite challenging to get usually, especially considering that TESS typically only views something for 27 days. That's a kind of a tight schedule to get RVs. Now, I've designed this experiment with a few requirements. First, we're selecting targets, and it's a small sample size, but we're selecting targets that have Kepler and TESS photometry. And perhaps more importantly, we choose targets each observing semester that will be getting additional TESS photometry that NEID can look at simultaneously with TESS. And finally, we're most interested in mitigating stellar variability. So we choose targets with some known activity. You can look at old photometry to find rotation signals, and actually all of my targets ended up having archival RVs as well. And we sort of extra prioritize targets that have variability in photometry and RVs, and if those two seem related. I include a little list of extra things that turned out to be the case for our targets, but are not necessary. Now, we ended up getting 8 targets for our sample, and these sort of naturally subdivided into known planet systems with published exoplanets with a mass, and these what we call modest variability systems with no known exoplanets, but this variability that's seen in the photometry and then also in the RVs. Now, our final goal is to perform an injection recovery analysis of these systems, basically test which photometric methods and which photometric data sets, when used, end up producing the best results and the most sensitivity to small terrestrial, probably, exoplanets around some of these systems. But the known planet systems in particular are really nice because we can benchmark our results by looking at how are our masses doing compared to published values. Now, I've talked a lot about Kepler and TESS, but what I haven't really motivated is why we're using NEID for this project. 2 reasons. The first is that NEID is Q-scheduled, which is a really nice thing about NEID because it allows us to get these simultaneous RVs with pretty high cadence in a way that conventional night scheduling would make pretty challenging. Second, of course, is, and there have been other talks on NEID, but that NEID is a precise instrument, in some cases getting better than 50 centimeters per second stability. And so as a result of that, we are going to be able to, hopefully, look at in really good detail at stars and what their variability and maybe planets look like under the 1 meter per second level. NEID makes it so that we can do this. Now, how are we doing so far? I include a sort of big plot here on the right, and I'll get to it in just a moment, but we have so far gotten 170 NEID RVs for this program that's been going on for a little while, and 68 of these are simultaneous with TESS. So you see on the right are 8 targets, and in these light blue windows are the TESS coverage that they received at some point during NEID observing semesters. The small gold dots are NEID radial velocities, and then I include a little bit of extra information about them as well. Now, it's a real shame that right as TESS was swinging back to the north and hitting the Kepler field again, we just started collecting RVs before the Contreras fire came and shut us down for a little bit. But all is not lost because TESS, while in the south right now, will be swinging back to the ecliptic in the fall. So we plan on getting more simultaneous RVs, in particular with our K2 targets, which will sort of continue this program. But we can do a lot of interesting preliminary analysis in the meantime because we have a lot of RVs. So this project is very ongoing, but I can share a little bit of the sort of tantalizing-ish results that we have. First, I want to talk about a system that a lot of people here may be familiar with. It's Kepler 21. This is a bright system, slightly evolved F-star. And in fact, it's the brightest planet hosting Kepler system. So like I said, a lot of people here probably know it for that reason. Now, it's got a short period, 3-ish day, rocky planet that was, of course, discovered with Kepler. But what's particularly interesting about this planet is it was one of the first known exoplanets that had a sort of rocky composition that was maybe consistent with Earth. And I say maybe because despite the fact that this is the brightest known Kepler system, we still have a mass measurement that's just a little bit shy of a 3 sigma confidence for this thing. And that's in no small part due to the stellar variability that's present in the system. Another target I want to bring up is HD 173701. Now, this target is a fair bit brighter, but it's probably not known to anybody here because it has no known planets, but it has a lot of archival high-res and APF data that have allowed me to perform some interesting analyses on this. And in particular, these in combination with photometry have revealed the fact that it seems that stellar variability in this system is evolving on short to long to medium length timescales in interesting ways. We also have discovered what we think to be a planet candidate in the system, but that's not really the focus of my project and my talk here, so I'll keep the discussion of that to a minimum. Now, for Kepler-21, what's great is that we have already started to increase the mass precision, perhaps unsurprisingly with additional NEID RVs, to almost 4 sigma for this system. But so far, our analysis has been restricted to basically a copy or something very similar to what was done in Lopez Morales et al. 2016, where this mass was most recently measured. Basically, we train our activity models on Kepler instead of training them, say, on newer TESS data. But we want to train them and see what happens when TESS is involved. And this is still ongoing. I wish I had some really cool results about that right now. But the reason sort of that we're interested in this especially is because they're seeing different things. Big surprise, an autocorrelation function to Kepler nicely reveals the likely true rotation period of the system. But on TESS, it's not doing so. It's not doing as well because 12 days is right around where TESS doesn't do so well with rotation periods. We're seeing 1/2 and 1/3 of the rotation period in a couple of different TESS sectors. And we think that it's possible that spot complexes are evolving on this, 10-year timescale, or it may just be that TESS is not sensitive. We want to probe and test this. And my brief little spiel about HD 173701 is that this is a Kepler system, no known planets, like I said before, and it's got a longer rotation period, include a little autocorrelation function done with SpinSpotter over here. But what's interesting is that if you look at the archival high-res and APFRVs, you see that there is the half-period frequency is dominating that RV time series. And if you look at Kepler, which was taken at a somewhat more similar time, you see that this activity modulation is evolving quite a lot, actually. You see in Q6, a 33, 34-day period dominating, and then in Q7, you see 1/2 and 1/3 of that period dominating. So it seems to be evolving on these weird timescales. And I'm running a little low on time, so I'm going to speed up a little bit. But basically, when you do an actual MCMC GP analysis, all the stuff, you get a weird bimodal distribution on just the archival RVs. You see the probably true rotation period, but even more significantly, you see 1/2 the rotation period. But when we include NEID data, suddenly this solidifies down to a 34-day period, the true rotation period of this thing. So we think that there actually might be some genuine evolution happening between these data sets because it has been 10 years since Kepler has observed this thing. Okay, so yeah, I'm out of time and I want to take questions. So I'm not going to do a really crazy run through of this, but yeah, that's my project and I hope people are interested. It's still ongoing. I'll take questions.
Good job keeping the time. All right, time for a couple questions.
Hi, great talk. I was wondering which TESS photometric reduction you're using to calculate these ACFs.
Sorry, sorry, I was looking for the speaker. Can you say that again?
Hi, which photometric reduction are you using to calculate these TESS autocorrelation functions?
We're starting with the PDC SIP flux, which again is also why you would not expect to see a longer rotation period on that. It would be great to get our own reduction that preserves longer period signals, but that's turned out to be a lot more work than I thought it would be.
Great, thanks.
Hi, thanks for the talk. What?
Oh, did I?
Sorry.
I accidentally clicked the thing.
Oh, okay. Sorry, Sharon. Okay, thanks for the talk. I was wondering if you could comment on how important you think photometric monitoring would be in terms of the faculae contribution, because we know for our sun that the faculae is really the big issue, but it's hard to see in photometry. Are you limited to only looking at spot dominated stars here, or is there a regime where you can transition, and what sort of precision do you need?
Well, I think that it is kind of a limitation. Our project is mainly focused on sort of spot modulation and that sort of thing. It's kind of the easiest for us to identify. So I guess I can't say, maybe I'm not seeing far enough, but I think it's difficult for me to say what the actual ability to apply this to faculae would be.
We have time for one more question. Did you get your microphone? No? Oh, you had the same question. Okay. Yeah, go ahead.
Hey, great talk. I just wanted to note that both of the systems that you highlighted have astroseismology, which bodes well for future characterization. And also this system 173701 has a well-known chromospheric activity cycle of 7 years. So.
Oh, I didn't know that actually. Yeah, a lot more deep dive. It's difficult because these systems are active, so there's kind of a lot going on in them. But that's good to know actually. They're bright, so I guess that kind of makes sense that they get a lot of study.
Great, let's thank Kari again.